Good afternoon, and thanks for coming. My name is Shyam Nair. I run the program management and product management for Azure DocumentDB, and with me is Andrew, my colleague. Between the two of us, what we're trying to do today is, kind of provide you an overview of DocumentDB as a cloud-born, NoSQL managed database service from Microsoft. And then Andrew will go into the details of some of the design patterns we have seen, some of the customer case studies. I think he's trying to do a demo too. The basic idea is, we want to highlight the technology, highlight the wonderful technology that we have built, as well as some of how customers have leveraged the platform at scale. So with that, I'll move quickly. So I think this is probably applicable for each one of us. Almost all of our life or work decisions today are very influenced and informed by data. Like the way we actually hike a ride, what we watch, the way we even play fantasy football is very driven by data. I don't know if you watched Satya's keynote. Satya talked about how you actually talk to an AI bot to figure out which is your dream team for fantasy football. And oftentimes, data is talked about as the new currency. The way I put it, I don't think data is the new currency. Data has always been the currency, but like the value of the dollar going up, value of data has been going up. And the currency also has been kind of expanding in terms of the volume. We have seen a lot of use cases today with respect to whether it's mobile apps, gaming, retailing, whether it's learning, new technologies, that data is actually influencing both line of business applications as well as consumer applications. A whole lot of the applications that we use today feels almost purpose-built for us and personalized for us, and that's driven by data. So the way I look at it, I think there are certain characteristics of data that's changing, or there's momentum around certain characteristics of data. One of which is schema-free. We have often talked about structured data as well as unstructured data. Even in the structured world of data, many of these applications currently deal with data and cannot adhere to one strict schema. The schema-agnostic nature of a database is very relevant for applications to actually leverage and build intelligence on. Along with variety is the volume of data. The amount of data consumed by applications, the amount of data generated by applications, whether it is IoT applications, whether it is telemetry, even the service that we run, the exabytes of data that we actually have that informs us in terms of providing better service to the world, the volume of data is actually increasing, and there's no sign of stoppage anywhere. Variety, volume, and then velocity. The speed at which these data is generated. We used to only keep the data that we required. Now we keep all the data we generate and then try to find intelligence out of them. So with the velocity of data, what customers are seeking is, hey, a high throughput system, predictable performance, and very low latency in terms of consuming the data and actually making your applications much more modernized. So out of all of this was born a built-for-cloud, NoSQL database fully managed by Microsoft, which is Azure DocumentDB. So what I will spend the next 5 to 10 minutes probably talking about some of the key characteristics of it and the design patterns in terms of why we built it and what it actually provides. Then Andrew will go into the details of, he's the smarter one, so he'll go into the details of how customers are actually using it, as well as he'll go into some more technical depth in terms of how we actually provide that kind of capabilities. As we are, many of us building applications or administering applications, one of the biggest things we look for is, hey, what happens if my app goes viral? What happens if, whether it's a line of business application or a consumer application, how do we make sure when my app becomes more successful, I actually have the infrastructure to support it? One of the key characteristics of Azure DocumentDB service is there is predictable performance. You can go ahead and define how much throughput you actually require, and we guarantee that you will always get the throughput. Behind the scenes, we have server-side partitioning for limitless scale. You can have your throughput, which we call as, it's configured through what is called as resource units that Andrew will go into a little bit more detail. You can go from hundreds of resource units to millions or tens of millions of resource units. And it's always guaranteed to you. If you want to scale in terms of partitioning, there's no limit in terms of the number of partitions you can actually have. On top of that, we have support for time to leave, so that if you want to actually age out old data, with automatically being done by the service, you can actually do that so that you can keep the relevant data for yourself. The next thing after predictable performance and scale that an application looks for is low latency. Databases often cannot guarantee low latency. Azure DocumentDB at a P99, which is for 99% of the queries, we can actually guarantee that all reads are 10 milliseconds or less, and writes are 15 milliseconds or less. How can we do this? Because it's of the database engine is actually a write-optimized, latch-free database engine that's running on top of solid-state drives. Along with low latency is the global distribution aspect of it. You can write to one region. You can replicate the data automatically across all Azure regions. We are almost there in every Azure region today. By end of the year, we will be available as part of every Azure region. So you can write data to one region, have the data replicate across all Azure regions, and your application can be location sensitive and actually read data where you can actually get low latency. So global distribution not only enables low latency, the built-in high availability within a region. I mean, we actually have multiple replicas for a database, so you have built-in high availability within a region. We take automatic backups online without any downtime, so that in case of whoop scenarios where you actually want to retrieve data, we can enable that. Along with that, automatic failover across regions. So even in the case of a regional disaster, you don't have to worry about it. Your application can automatically failover. You can also do the failover manually, and everything that I'm talking about is available to you at your fingertip, whether it is elasticity, whether it is geo-distribution, using the Azure portal or through REST APIs. Next up, hey, what do I have to do with my application in terms of how do I actually query? DocumentDB supports query both using ANSI SQL as well as JavaScript. It's a JSON database. Every document actually is stored as a JSON, and as we are ingesting the document, there is no need of defining any secondary indices. We actually, as we are ingesting, we are creating indices. So you will actually get query performance out of it. We speak Mongo protocol. So if our application is actually written towards MongoDB, I mean, we'll be extending this protocol support in the future. But if you're talking towards MongoDB, you can actually have the application talk to DocumentDB, and we are able to talk the Mongo protocol. SDKs, we support Java, .NET, Python, and Node.js. And we are continuously innovating and actually adding more support for languages. So it speaks your language, whether you want to define stored procedures, whether you want to define user-defined functions in your and run it within the database engine. It's possible to do that. Just do that in JavaScript. Now, the other aspect of that, when you're betting on a database, the other thing that you need is enterprise grade, not just in SLAs, but in terms of security, in terms of compliance. Azure DocumentDB is part of Azure. It's available in all Azure regions in hyperscale cloud, which is enterprise grade cloud. Azure DocumentDB itself provides 4 nines SLA, which is industry leading. We also guarantee throughput, consistency, as well as low latency, as I talked about. Our compliance certifications are growing. Over the course of this year, we will be compliant with all the Azure compliance certifications, and there's built-in security through the Azure model. So in summary, before I actually hand it over to Andrew, what I want to talk about is, think about Azure DocumentDB as it's actually a planet scale, NoSQL database, globally distributed, with elasticity built in, low latency built in, availability built in, consistency, and global scale. Now, all of this is supported by an enterprise grade SLA. So I'll let Andrew actually talk into more of the details of how some of our customers have actually used Azure DocumentDB, some of the patterns that we have seen. And again, we are using certain examples. It doesn't mean that these are the only examples or the only case studies that we actually have, but it's more about emphasizing some of the key design patterns and enabling you to actually build applications using Azure DocumentDB. Andrew, to you.
Awesome. Thanks. Hey, before I get started, I just kind of wanted to get a feel, like how many of you guys have played with DocumentDB before? Oh, awesome. And how many of you guys have played with any kind of NoSQL database before? Oh, awesome. That is fantastic. So one of the first things I normally want to just make sure and convey is, when is DocumentDB a good fit? Because as you've noticed throughout this conference, we've been bombarding you with so many different data products. But I mean, the short story is, when I also talk about JSON, and this is a document-oriented database, I'm talking about JSON documents. So if you're here to learn about how to store Word documents, PDF documents, I'm sorry. I think there are some pretty good sessions on OneDrive and SharePoint here at the conference. But here, what I really want to talk about is JSON documents, all right? Just to make sure we're on the same page. Now, the way I like to think about how this fits into the Azure family is I like to go back to this famous quote. It's called Maslow's hammer. It was published back in like 1966 in, I think, the Science of Psychology journal. But basically, Maslow says, if all you have is a hammer, everything looks like a nail. And what I believe is, for the last couple decades, we have been using relational databases as that hammer. Why? Because that's pretty much all we had, right? We're all familiar with the traditional three-tier architecture where we have a client, a server, and a database. But the thing is, as time has gone on, we have introduced, we have seen a lot of new problems that the traditional three-tier architecture and our trusty hammer are no longer able to cope with. And this is why Azure has built this awesome data platform with all of these different products in order to fit every scenario and solve every problem that you have, right? And a lot of the new challenges that we've brought to you instead are, we have built such a vast toolkit and so many tools that now a lot of the challenge is learning how do you choose the right tools for the right job. And if there's anything that you take away from my talk today, I really hope that, you learn when is DocumentDB a good fit for you, and what are some of the patterns that you can use to achieve success. But at the end of the day, I want to make sure that you are picking the right tools for the right job. So with that said, Sean mentioned the problems of variety, volume, and velocity. These are actually the 3 V's that were presented by Gartner in a paper called, I think, The Challenges of Big Data. And I'll tell you a little bit about, what do these actually mean, right? They're not just buzzwords. They actually have some meaning behind them. And the way I like to think about variety is, let's start with a scenario, just to give you kind of a concrete idea of what this means. Let's say I am building a product catalog for a major e-commerce website. And what I want to do is I want to be able to query all of my products in my product catalog by various attributes, right? This is the main thing that a database really provides. And what we're going to do is we're going to use our trusty hammer, our relational database, and try to build our product catalog. And then I'll show you how we can do it even better. To start off, I have a couple of mugs here that I'm going to sell in my product catalog. And I have a set of attributes, right? I can query back my mugs from my product catalog by the color, by whether it's microwave safe, by how much liquid it can hold. Now, the thing is that along comes my next product, and I sell everything, right? I sell everything under the sun. I sell mugs. I sell laptops. And along comes a Surface Book, and I'm wondering, oh, I get that I have color here, and it appears to be gray, but what do I put for microwave safe or liquid capacity, right? And this is a silly question, but I will note, please do not microwave your Surface Book. Don't microwave your laptop. It's a bad idea. Don't do it. But my real point here is, you know what? It turns out mugs are not laptops. That's pretty obvious. But how would we model this, right? And what I'm going to do here is I'm going to use my intuition. I'm going to take a few new naive approaches on how I would actually model this data in a product catalog. But at least for this approach right here, don't try this at home. This is not how you would do it in a relational database. But this is my intuition, right? So my first intuition is, OK, I want to be able to query my Surface Book by the processor, by the amount of memory it has, by the amount of storage it has. And the thing is that, the way I'll do that is I could, when I have approaches, I'll just create a few new columns. I'll index them. And that way I can serve those back efficiently via a query. The problem here is, this doesn't seem like a very efficient use of space here. What I'm doing is, as I add more and more product types, I'm going to have more and more product attributes. And at the end of the day, I'm going to have a very sparsely filled table. And this is just not a good approach. So I'm going to use my intuition, and I'm going to come up with one approach that's even better, right? I'm going to create tables for every one of my product types. And now life is good. Now I've separated and abstracted out my mugs from my laptops. But here's the thing, right? What if I have 100,000 product types? What if I have 100 million different product types? Maintaining 100 million tables is not something I enjoy doing. I assume this is something that you guys also don't enjoy doing. And then furthermore, even for a given product type, in my pocket, I have a really nice smartphone. It has Bluetooth. It has NFC. I could create columns for, let's say, the type of NFC and Bluetooth radios it has. But what if I'm also selling, cell phones from every from every year. And I still have my Nokia Lumia 3310, my trusty, you guys remember this phone, right? This thing was solid as a tank. It, you only had to charge it like once a week. But the thing is that what kind of NFC radio does that have? Oh, that doesn't really make sense. And why do I actually have to define a schema across all cell phones saying, you know what, every phone now needs to have this NFC radio or Bluetooth property, right? And so here's how you would actually solve this with your trusty hammer with your relational database, right? What you would do is you'd probably abstract this out into a products table, a product attributes table. On the product attributes table, you'd put a foreign key back to the products table so that you can perform a join on that. And then you would create a column for the attribute, a column for the value. And then you'll have a query at the end of the day that looks something like select star for my products, enter join product attributes, where attribute equals, let's say, microwave safe, and value equals yes. And you know what? Microsoft has done an excellent job over the past couple of decades on making sure that joins are incredibly, incredibly efficient, that there's minimal overhead. But you know what? We can do even better than this. And this is where JSON is, I think, beautiful, right? If you look at the left-hand side of this JSON, what I have here is the JSON records for my mugs, as well as a JSON record for my laptop. And on the left-hand side, you'll see that I have a bunch of attributes: name, color, capacity, microwave safe. JSON is self-describing. And what this allows me to do is add and remove attributes on a per record basis rather on a table basis. I have now per record schema rather than per table schema. And this allows me to handle heterogeneous data much, much easier. In fact, JSON also allows me to do some powerful new things, like I can denormalize data and exploit data locality so that I can pull back all of these other attributes. Let's say I want to store like some options in an array for the processor for this laptop, or for capacity, I even want to expand that out to, let's say, value units. I want to have nested objects. I can do that. This will all be local within a single record. And when I do a point read, this will all come back incredibly efficiently. Now, the other two problems I mentioned, volume and velocity. What does that mean, right? So volume is I have so much data, it no longer fits on a single box. Velocity is I have so much throughput, I have so much requests per second. If I were to put this on a single box, that CPU is going to catch fire. That memory is not enough. I don't have enough I/O. So let's talk about problems of scale. And the way I like to think about scale is, let's talk about a story about one of our customers. What we did was we partnered with this game studio called Next Games to build a free-to-play iOS game called Walking Dead No Man's Land. And really, I think every story is better with zombies. I think zombies should be mandatory, right? It's just awesome. So here, I'll have a short video to give you some context. Let's see. How does volume work for this? Hey, can you up the volume on?
We can actually provide new content after each episode within 24 hours. I pretty much knew that with choosing Azure and Microsoft, I would be guaranteed with better support than I would get from any other cloud providers. We know that there's somebody there looking after us. In Azure, we have, I don't know how many hundreds of servers, but then again, why would I care? It's cloud. The latest addition that we've been starting to use in Azure is DocumentDB, which has really helped us to make our development cycles faster, and that actually enabled us to create a very engaging player versus player experience within the game. Many of the things that we would usually need when we're doing backend are already pre-figured out for us by Microsoft. And we were able to deliver such a high quality, engaging game with stunning graphics, good gameplay, and reliable technology.
So, I mean, I want to talk about some of the interesting challenges it takes to build a game and how the challenges relate to persistence. So one of the interesting things about a game is, you know what, the traffic doesn't actually grow over time. Games actually don't age as gracefully as most other apps. Like, I built a database today, and I can tell you what happens over time is, over time we get more users, we get more requests per second, we need to serve more throughput. Not a lot of people actually play games, 10 years out. And so instead what happens is you do this huge PR marketing push for a game, and then you open up the floodgates when you launch, right? And here's one of the scary things about when you launch. It's really, really hard to actually predict just how much throughput you need to be able to serve. And what's even worse is if you get this wrong, you don't really get a second chance. If you botch up your launch, you might kill all hype for your game. You've done all this PR and development work for nothing, and that's a very, very tragic thing to have happen. And so what you need to be able to do is you need to be able to scale from day one and to handle very unpredictable, bursty traffic, and you need to be able to do this at scale. Now, some of the other challenges that Next Games had was, for a game, I mean, it's great and all that you've built all this hype and you want to, you have all these users coming in on day one, but you know what? You don't want them all leaving on day one either, right? And one of the easy ways of retaining users is you build a nice social experience. And what you do is that way you can kind of rely on network effects to help retain users, keep them more engaged. And you can do this through building kind of a social experience around guilds, clans where friends can play together, and then expose leaderboards and incite some competition to make sure that, you know what, if Sham beats my score tomorrow, there's no way I'm going to let him keep that score above me. I'm going to go ahead and beat his score right back. But this introduces a few new challenges on your persistence layer. Really, it all comes down to having really, really low latency. Because if you ever play a game where even your ping, if you're looking at like a couple 100-millisecond latency on a game, that's a very laggy game. It's not a very good experience. And this really kills the game. And so if your database now takes 100 milliseconds or a second to perform a query, that's a showstopper. And so what you really need is really, really tight latencies, like single-digit millisecond latencies. And some of the other things that at least Next Games found to be challenging is not only did they have to handle scale, but they also had a tight timeline to launch this game. They wanted to launch it when the Walking Dead season started last year. And if they missed that launch, that'll also really hurt their create flow. And so they needed to be able to move fast without breaking things. They needed to be able to iterate and have a very flexible data model. Now, the results for this game are actually phenomenal. They launched last year, right as the Walking Dead season started. They reached #1 in the iOS App Store on their very first week of launch. And within their first week, they had well over 1 million game downloads, and they were performing roughly 1 billion queries per day against DocumentDB. But I think what was really impressive, even more from my end, since I'm a database geek, was 99% of those queries were being served with single-digit millisecond latencies. That's amazing. 1 billion queries per day with 99% at 1 millisecond, or single-digit millisecond latencies. So how do you do this, right? I want to build a #1 game in the iOS store too. Well, I mean, maybe you just throw some data in a database and you walk away and you go, oh, data is easy, right? Well, it turns out this is not so easy. And let me tell you about some of the problems and how they kind of evaluated, which tool should they use for this job. One of the first things you normally go to is caching, right? When you go, oh, low latency, what I need is an in-memory cache. The problem with this approach for them was if you have a leaderboard showing everyone's score, and every single one of those players is constantly ticking up their score, then I'm constantly invalidating that record for that leaderboard. In fact, it's being invalidated even more frequently than it's being read. So caching is kind of out of the picture. Then you go, well, OK, so I can't cache this, so I'll just rely on the database itself to be very, very snappy. It can scale. It can deliver very low latencies. And so they started looking around at all of the various offerings that Azure has. And what they saw with relational databases, their trusty hammer is, they have so much throughput that they needed a shard because it could not be served by a single node. Now, sharding is not too bad when you have 2 nodes, when you have 3 nodes. It's a real pain if you have 100 nodes, 200 nodes. What ends up happening is you gain a lot of new overhead in terms of schema and index management. When you want to iterate quickly on the application and you need to now apply a schema or index update across 100 nodes with very, very short time to actually deploy this and always be available, that's a hard problem. And even worse, now you also lose some of your relational benefits, right? So if you need to do, one of the strong things about relational databases is it supports a relational model. But if you want to do a join across 2 separate physical nodes, you're now serving one network request out of one node, looking at that reference, and then going to another physical node. And this is going to be slow. It's going to be inefficient. So they started looking at some of the NoSQL stores that Azure has to offer. And what they found was a lot of at least the key value stores that they looked at, didn't have the throughput and characteristics or latency characters that they needed. But even worse was the need for secondary indices. For them, they also query back a lot of these documents, not just by a player ID, but by a third-party auth provider like the Google ID or the Facebook ID for login by Google, login by Facebook. And so this is where DocumentDB kind of became a really good fit for them. I mean, what we did was we have a database designed from the ground up to scale out. And this is to support many, many gigabytes, hundreds of gigabytes, terabytes, hundreds of terabytes, and millions of requests per second. It's highly performant, delivers very low latency, removes the friction around indexing because we can automatically index every property in every document without even knowing what the schema is ahead of time. And let's talk about why this fit in so well. Fact, like I mentioned, sharding is a really, really painful problem. And I mean, this is one of the things where DocumentDB has done a lot of work to make this a really painless experience. Now, the way it works is we actually manage all of the physical partitions needed to serve your workload. And we do this by measuring two different dimensions. One is the amount of storage you need, and the other is by looking at how much throughput you need, how many requests per second you need. Now, the way our model works is storage is on a consumption model, and throughput, what we do is you can reserve the amount of throughput. And this is really to help safeguard you against one of the big problems in cloud computing and multi-tenant services, which is noisy neighbor problems, right? If you ever have a multi-tenant cloud service, what you might run into if resource governance is lacking is one tenant decides to bombard the service with a lot of requests. It uses up all of the CPU and memory, and all of the other tenants go, hey, why am I seeing degraded performance here, right? And so what DocumentDB does is we have you reserve an amount of system resources, and you can dynamically scale down, and we guarantee that whatever you have reserved, we always deliver. We make sure that that is incredibly predictable. Now, the way we do this, because every query is different, every request is different, right? A create does not take the same amount of resources as a read or a delete, is we have this thing called request units. Now, basically, this is a logical abstraction on top of all of the physical resources it takes to perform a request, and that's in terms of CPU, memory, I/O. This is actually the most important metric you will want to know about DocumentDB once you get started. But some of the value that this brings, a lot of people go and ask me, like, hey, man, like, this request unit concept, this is really kind of confusing. Like, why do we do this? Well, if I were to put this in context of, let's say you are managing your own on-prem servers or virtual machines, and you're told, tomorrow I need to scale up from 1 million requests per second to 2 million requests per second. What do you do, right? I can just blindly add more nodes, but really the bottleneck, it might be CPU, it might be memory, and then you go, well, what is that bottleneck? So you might stress the system, you might go, okay, I think the bottleneck today is memory, but then you go, oh man, how much memory translates to how many requests per second? Right? Like, this is a really, really hard problem. And what you do is you might just throw some memory at the system, you stress it again, and you go, did I hit my target? Oh, maybe not. What's the bottleneck now? And let's keep trying to hit our target RPS. Now, with request units, this is actually really kind of cool. What we do is when you send us a request, we actually return back the charge of that request in terms of request units, and we make sure that's predictable. So if I create requests on a document that looks like a sample document, it takes, let's say, 5 request units. We guarantee you that tomorrow it'll cost 5 request units, and a year out it'll still cost no more than 5 request units. This allows you to do capacity planning really easily. If I need to do, let's say, 1 million of these concurrently, I just go, okay, I know how much request units it takes per request. I know how many requests per second I need to serve. I multiply these two values. That's how many RU per second I need to provision. And tomorrow, if I need to double that, great, just dial up the amount that you've reserved and double that, right? Super simple, super straightforward. Now, the way we now do this in a distributed system is we need to be able to partition this across many, many different nodes. And what ends up happening is you will need to give us a hint, but this is the only thing you need to do. You don't need to do any shard management. We handle all of the rebalancing. We handle all of the routing. The only thing you need to tell us is a partition key, which is a hint for us on knowing how do we partition that data across nodes. And you can do this programmatically. You can do this through our portal. In this case, I have a short code snippet from our SDK. And what I'm doing here is I'm creating a new collection. I'm saying, hey, I want to put a partition key on this path walker ID, and then I want to reserve this amount of throughput on this collection. Now, for that throughput, what's really cool is that's also mutable. So tomorrow, if I need to dial up, I need to dial down, I can send a update collection request, or I can go into the portal and just change the value, and I can dynamically allocate more or less throughput, scale up, scale down elastically, and DocumentDB will handle all of the shard management for you. I think that's really beautiful. The other thing that was a really big hit for for gaming is most games have a global user base. Now, there's this really, really hard problem. It's kind of a physics problem where if you have a global user base, let's say your database is in North America and you have a user in Australia, you now have this crappy bottleneck called the speed of light. And really, like a packet can only travel across a wire so fast, right? It's bounded by speed of light. And even under ideal network conditions, the network latency between North America and Australia is going to be something like 300 milliseconds. Totally unacceptable for a game that needs to be able to deliver a very low latency, lag-free experience. Now, what's really cool is not only does DocumentDB allow you to replicate to, let's say, another region for, let's say, disaster recovery. So if tomorrow some zombies, the zombie problem actually becomes real and they wipe out a data center, so you want to automatically fail over to another data center. I mean, you'll at least not have to worry about your data. You might worry about zombies, but at least disaster recovery is already taken care of for you. But we go one step further than that, and we allow you to replicate to n other regions. So rather than us choosing a region of our choice, you can choose, let's say, 10 other regions, 15 other regions, replicate your data to data centers around the globe. And then this allows you to cheat the speed of light, because what happens is now when that user in Australia makes a network request, I'm not sending that packet all the way to North America and all the way back. Instead, he's talking to a data center near him. And what's really cool about this is when you talk about replication in distributed systems, one of the things that often comes up is, well, what's the consistency model for this, right? A lot of systems are either eventually consistent or strongly consistent, and they don't really give you a lot of options on how do you configure that. Now, what I think is really cool is not only do we give you the ability to replicate to many regions, but we also allow you to tune that consistency on your account. And what you can do is we give you even a few click stops in between strong and eventual consistency so that we have these concepts of session consistency and bounded staleness. And the way these two work is, for eventually consistent systems, what happens is I might asynchronously replicate to another replica. And then when if I were to serve a request out of one of the replicas, what ends up happening is I want to make sure that my application is very snappy, it's very responsive. I'll just directly serve that read from that replica. But the thing is that I might get a stale read, right? And a real concrete scenario around this is if I'm building an application like a social news application where people can comment, let's say it's something like that looks like Facebook. If I read a comment and then I refresh the page, that comment might now disappear. And I'm going and wondering, I thought I sent in a comment. Where did that go? Did something, did something happen to it? Should I comment again? And then I refresh the page and it suddenly shows up. Well, for eventual consistency, I mean, this adds a lot of programming overhead now, right? You might need to write in your session that, hey, I know that this comment was posted. I already got an ACK from my persistence layer. But you know what? We make that easy for you. So the concept of session consistency is the client can establish a session to the database. And every time I write, basically the equivalent to a log sequence number gets responded back to the client. And now whenever I do a follow-up read request, I say, hey, I know that I at least have seen this log sequence number. Whatever read you send back to me needs to at least reflect that, right? And so this is the concept of you always get to read your own writes, and you do not get stale reads for your own writes. For bounded staleness, we also allow you to put bounds on just how stale the data can get before we apply back pressure back to writes. And this is also, I think, really nice in that when you're dealing with eventually consistent systems, just how eventual is okay, right? Like, I mean, is years okay? Is days okay? Realistically, I mean, for DocumentDB, I don't think you'll ever, realistically, like in practice, never see something lag behind more than like 10 minutes. But for bounded staleness, you can tighten that up and say, like, you know what? I want to, I can only tolerate a minute or even like half a second on how stale that data can get in my replicas before applying back pressure to writes. So I think this is really cool that, you know, I'm a database geek. We really wanted to build a database for geeks and give you all the little knobs to tune consistency levels. Now, some of the neat things here are all of the replicas are actually bound under a single endpoint. And then what you can do here is you can set preferred locations programmatically using our SDK. And so the model for delivering low latency around the globe looks something like this. If I have users all around the world, I might have an application server that's hidden behind Traffic Manager, and that application server is deployed around the globe. Now, when that user is in Australia and he hits that Traffic Manager, he'll go, oh, OK, I will route you to an app server that's located in Australia. And the app server in Australia understands that, hey, you know what? I'm in Australia. Let me put in the SDK that I prefer serving all of my reads out of Australia. Now, if another user comes in and they're located near our East US data center, they hit that application server. They see that the application server is aware that it's in East US. And in the code deployed for that one, it goes, hey, you know what? My preferred location is East US. And this allows you to now deliver very low latencies on a global user base, and also give you kind of a demo of what this looks like in practice. Let me switch over. So here I'm in the Azure portal. I have a set of database accounts, DocumentDB database accounts. I'll show you just how easy it is to set up global replication. Here I have an account that I've already created, and right now it's in one region, it's in West US. Normally when you think about geo-replication, if you were to do this in a do-it-yourself model, you're spending days implementing this. Check this out. Let's say I want to replicate this to East US, West Europe, and Japan. I click on those regions, and I hit save. And you know what? In a couple minutes, I will have a globally replicated database. That's phenomenal. Now, what's really cool here is I also have, and this normally takes just a couple minutes, depending on the size of your data. If you have a lot of data, it can take a little bit longer. But here I have another account that I've already pre-configured, and it's available in 13 different regions. And what I have here is also a web application. And what I'm doing here is I have 13 worker roles deployed around the world in each of these 13 regions. And each of them are doing a bunch of read and write requests and spitting back how much latency it took to serve that request. Now, if you notice here, the blue line, the read latency. Oh, by the way, I'm totally a database developer. Sorry, my my UI skills are still I'm still working on them. But this really helps illustrate the point. If you look at the graphs here, the read latencies are all single-digit millisecond latencies. So here, let me show only read latencies on my graph. Well, it's the blue line, and what you notice is because those are delivered with single-digit millisecond latencies, that you don't even see them anymore on this graph. They're very, very low. Here, let me just refresh the page to show you that. And on the bottom of all of these graphs, what I have here is a little table, and this is kind of my cheat sheet just to show you under ideal network state, what it typically takes to do a round trip between two regions. Okay, so here I have all my read latencies. Notice that I'm now delivering under a single data set, single-digit millisecond latencies around the globe. When I look at write latencies, what you'll see here is, oh, my write latencies are a bit higher because today what I have is I have a single write region, and I can read in all of these regions local to that data center. However, writes I have to go to a primary. And today my current write region is Japan East. So you'll notice that this actually follows pretty closely to what my table here is. The latency between West US and Japan is roughly 100 milliseconds. Now here's what's also really cool is I can now do a manual failover. Let's say I also want to dynamically change my write region, because what I want to do is I want to change that write region to follow the globe. And what happens is I've noticed my traffic pattern in my application that when Japan is in daytime hours, I see most of my traffic in that region. And then when it's nighttime in Japan and it's daytime in the US, what I want to do is most of my traffic is in the US. I want to serve my traffic out of there for writes. What I can do is I can go to the portal. I can do a manual failover, which changes the write region. And I can dynamically configure this now to use East US as its primary write region. I do a manual failover, and what will happen is, it'll take about a minute, you'll see a big change in the latency graphs. And you should see Japan East go up, and the latency for, what did I choose? I think it was East US. East US will go down. And this takes roughly a minute. So while this happens, I'll also kind of talk through some of the cool things you can do here. So what I did here was a manual failover, but you can also set up failover priorities for automatic failover. So let me open up my other database account and show you how you can configure that. So if you want to, let's say, use automatic failover to safeguard you against zombie attacks, I go into an account, I hit my, my regions. Oh, this one I also just recently configured. You can set failover priorities, and what the failover priorities allow you to do is you go, you know what, I don't want Azure just to randomly pick a random data center to failover. I can actually set a priority queue of, hey, you know what, if my primary region is West US, I want you to use East US as my next failover, and if that one also gets taken over by zombies, I'm a little bit concerned, but I want you to now use, let's say, Europe as my next failover. And you can set an entire queue of what regions you want to failover. And it looks like here my failover is complete for this application. And as you can see, I've now changed the write region from Japan East to East US. My latency in East US for writes is now single-digit millisecond latencies, and Japan has now creeped up to basically the speed of light, the time it takes to do a round trip. I think this is really, really cool. Now, let me go back to the presentation. So I kind of talked about some of the scenarios that are what we've seen to be common patterns, common use cases for DocumentDB. And what we're doing is we actually just, I kind of cheated here. I didn't come up and brainstorm like, oh, what are good scenarios for DocumentDB? I just cheated and looked at what, who are our customers today and what are they doing? And I talked a little bit about product catalogs in retail. I talked a little bit about social gameplay and gaming. But two other areas that we found to be amazingly good fits for DocumentDB are IoT scenarios in which what you need is a raw event store or a device registry. And we've also seen a big tick in this social analytics and ad tech space for storing user behavior telemetry, as well as third-party data from crawlers or third-party social feeds. And what I'll do is I'll tell you a little bit about the challenges for each of these other spaces and tell you a little bit about what our customers are doing. For IoT, one of the big reasons why DocumentDB is a good space is it turns out, hardware is, relative to software, pretty hard to update. what ends up happening is each time I deploy some sensors or some hardware out into the field, each generation of those devices may have different sensors. And over time, what ends up happening is I have many different generations of sensors deployed out there with varying sensors and varying telemetry being emitted from that. And so what I have here is basically every device might have different schema, and I need a system that is flexible and schema agnostic to be able to ingest that and be able to serve queries back out of that data model. Furthermore, I might have lots and lots of sensors out there in the field, and if each of these are emitting telemetry, let's say every second, I'm now dealing with a very high rate of ingestion, and so now I have the problems that I've described in volume and velocity. I have lots of data and a lot of it coming in very quickly. So one of the customers that we're working with, they're a top 5 automotive manufacturer in the world. And what they're doing is they're building a connected car scenario for their, all the cars that they sell. And the value that they provide now down to their customers is in the connected car, if you were to get into, let's say, a car accident, there are sensors that tell you when an airbag gets deployed. And you know what? If I'm in a bad car accident, I might not be in a good state to call emergency services for help. And so their system will automatically detect, hey, the car has been involved in a bad accident, airbags have been deployed. Let me automatically notify emergency services for you on your behalf and send that to your vehicle. And I have sensors for GPS telling EMS, where is the car? It also has diagnostic services. They provide that in the form of like monthly health reports on your vehicle. If you have a relatively new vehicle, I've noticed this is becoming more and more popular amongst different auto manufacturers. And what they'll tell you is like, hey, we have oil temperature sensors. We have sensors for all the various different components. And what I will do is tell you, you know what, if something is looking a little bit off, please come in for service, and we'll get that fixed for you right away. This is also very useful for them in terms of collecting telemetry on their end for product development and helping them iterate and go, hey, we know what the common components that fail are. For the next generation of vehicles, those will get even better. And lastly, some of the things that they do is it's bi-directional communication, and they can do also provide remote service, where if you lock yourself out of the car, you give them a call, and they can actually unlock the car for you. Now, the thing is that each of these cars have many, many sensors, and this is actually a really large automotive manufacturer, so they have cars just all over out there, each with producing their own different records. Like different models of their car lineup have different sensors, different capabilities, and even new generations, new years, they're adding things like cameras and radar for doing assisted cruise control, lane departure, and really this is just a lot of data, heterogeneous data coming in, and they needed something that can handle that kind of scale. And so this is a simplified view of what their architecture looks like. But this does a pretty good job of showing you all the meaty parts. And what they do is they have all of these cars emitting to a single inbound interface that is a web API. And what they're doing is they're storing the raw events directly into DocumentDB. But the thing is that because these are raw events, this grows very, very large. And what they do is they set a TTL on that to make sure that over time this doesn't get too costly. TTL is time to live. What they also do is they emit this out to an event hub, like a message queue, and they have a stream processor that does time window aggregates. So what they can do is they can see, what is the min, max, average across many records for a given time. And what they do is they double write this out to DocumentDB as well as blob storage. And what they use is for the aggregated event store in DocumentDB is this is a warm store where they now have a bunch of dashboards hooked up, monitoring, hey, what is the aggregate view? And when they see an anomaly, they go, hey, I see a huge spike here. This looks kind of weird. They can now go back and query the hot store, the raw event store, and go and look at each individual record. Hey, what happened here? Let me look at, was it one device? Was it multiple devices? What are all the different properties that can give me some clues on what happened? And the reason why they use blob storage is to help drive down costs. They use that as a cold store. It doesn't need to be latency sensitive, nor does it need to deliver queries. They use the warm store for that. But this kind of gives you an idea of their architecture. If any of you guys are familiar with Lambda architecture, by the way, this probably looks really familiar to you. This is just classic Lambda architecture. It's a pretty common pattern today. Anyhow, this doesn't have to just be applied to cars. If you have, let's say, temperature sensors in a manufacturing plant, and you want to make sure that, if tomorrow, the climate system, the climate control system is out of whack, I need to be able to detect that and act on it quickly. This is also a very good pattern for you to apply. This really applies for all sorts of different IoT scenarios. The other one I mentioned is social analytics and ad technology. And some of the things challenges that they saw was they're ingesting data from a lot of both third-party sources like Twitter, like Facebook, as well as they have some web crawlers of their own that help scrape pages and get a deeper look on that. When you're dealing with third-party data, who gets to dictate the schema, right? It's not you, it's the third party, and they can change that at you at will. And if you're doing something like calling their REST API, getting some JSON and extracting that and fitting that into a tabular model, tomorrow if they change that schema, you might lose some data, and that's not a good thing to have happen to you. And so being able to ingest third-party data that's schema agnostic, as well as being able to query over that, this is the problem of variety that I mentioned earlier. And some of the other challenges for them are they have lots and lots of social and user profiles to deal with, producing lots and lots of content, and this gives them a very high rate of ingestion. So basically the same problems that I had discussed before. And one of the customers that we're working with in this space is this startup called Affinio. They were actually a startup using DynamoDB and Elasticsearch over at AWS. And what they found was, one, this system was very, very complex. And two, they were having trouble scaling this. And this is why they came over and started using DocumentDB. But what their scenario is they help you, their customers, analyze billions of social profiles. They look at all of the network connections, and they're able to build a social fingerprint for each of these users. And then they go a little, one step further, and they start to extract some knowledge and cultural insights on just what these people are up to. A scenario is, let's say I'm one of Affinio's customers. I run an athletic apparel company called Contoso Apparel. And what I want to do is I want to get an idea of, who are my customers? What they can do is they can look at all of the different profiles, social profiles following their social accounts, and they go, hey, I have a big following amongst soccer moms and amongst athletes. And then I want to know, okay, now that I know that I have a large following amongst soccer moms, what are they doing? What are they sharing on Twitter? What are they following? What are they engaging with? And give me an idea of what's trending amongst that segment of customers, and let me then build some collateral and help market in that space and really target that, right? I can really get a deep understanding of my customers there. And so what they're doing with DocumentDB is they're storing a lot of these tweets, geolocation data, some machine learning results, as well as scraped pages into DocDB. Now, the data from each of these different producers, the schema evolves independently. And so, as I mentioned, this is the problem of variety. This was a good fit for them. And as a startup, they also need to be able to iterate rapidly. And so the automatic indexing story was really nice for them, as well as the fact that we have a managed service. They're not spending days doing DevOps, maintaining their servers. Instead, they get to really focus on solving all of the other hard challenges of big data, of how do I model my data? How do I integrate all of these services together? How do I develop my application? Take the tedious work out, and they're able to scale this to over 1 billion social media profiles, or that's what they have today. I'm sure they aspire to even go into multi-billion profiles, and they're right now ingesting over 50 million tweets per day. And so they're really dealing with a large volume of ingestion here. Some of the patterns to take away from this so that you can also replicate their success is one of the big things about DocumentDB, as I mentioned, we provide scale out in the form of partitioned collections. One of the things that you'll need to be able to do is, or the only thing you really need to think about is, how do I want to partition my data, right? What is the partition key? So let's talk a little bit more about that. And basically what happens behind the scenes is once you've defined a partition key, what we will do is we'll hash that partition key and then distribute that to create a pseudo-random distribution, and then start putting those into physical partitions. And this is a dynamic number of physical partitions, so that if for any reason one of your partition key values is hot or grows to be very large, and we have packed other partition keys with that, we will handle that rebalancing and data movement for you. The important thing for you to take away is you should have a good distribution of data amongst the partition key values themselves. We'll handle all of the physical partitions on our end. And what I have is here an example where I've chosen the partition key for some data set is city. And as you can see, like some cities might have more data, some might have less data. And what I want to talk through is, how do you choose a good partition key? Now, there's no like one rule, that fits everyone when choosing how to partition your data. And the first thing you always want to start out with is looking at your workload. Is your workload read heavy? Is it write heavy? And the reason why I say you want to start with this is because this can stretch you into two different extremes, right? If you have a write heavy workload, what you want to do is you want to split that workload into as many partitions as possible, and so that you can maximize throughput. However, if you have a read heavy workload, you want to make sure that each of those queries can be routed to a single partition, that you don't need to fan out and serve the query from every partition in order to also maximize throughput on a read-heavy workload. Some other good characteristics just to call out: each partition key is given 10 gigabytes of space maximum. And so what you want to do is you want to choose a partition key that is fine-grained enough that it is much less than 10 gigabytes. And there's some pretty good patterns around this too. An example is if I have a multi-tenant system and I choose a partition key that's a tenant ID, what I can do is I can go, even though that this tenant will have more than 10 gigabytes of data, they have data split across, let's say, 10 different entity types. And all of those queries I do on a given tenant ID plus a entity type, right? So what I do is I form a composite key, and using that, I can now, if I have 10 different entities, I can split this out across 10 different partition keys. And this allows me to store much more data for that tenant. The other thing to note is DocumentDB actually does support multi-record transactions. This is actually quite unique in the NoSQL space. And I think this is actually quite novel. Like a lot of NoSQL databases give you ACID semantics around a single document or a single record. DocumentDB allows you to perform transactions over multiple records in the form of stored procedures, but those are scoped to a partition key, and therefore what you'll want to also think about is, what do my transactions look like? I should think about that when designing my partition key. Bringing this back to Affinio, here is some sample JSON. This is just a sample record from their scenario, and what I have here is a Twitter status message. And what I've highlighted here are some of the candidate partition keys that they looked at and that we helped them design through. The first thing they looked at was, could we fit a partition key around time? Because if you're familiar with range partitioning and aging out documents, it's probably one of the things you'll go to. The problem with this approach is if you partition by time, if all of your records come in, let's say at this time interval, and then this next time interval, and this next time interval, you end up sending all of your writes to the same partition key value, and then you end up with a very hot partition. And so given a write-heavy workload, time is not always actually, in fact, in this case, was not a very good fit to be chosen as the partition key. The next thing they looked at was a Twitter status message ID. For the message ID, this gives you a very, very nice distribution amongst many, many partition key values, right? Basically, every message has its own partition key value. The problem with this approach is when you want to go back and read that data, one of the issues is, how do you serve that query? Because I don't know the message ID always. Instead, my workload, or their workload, what it looked like was they wanted to pull back all the tweets for a given user. And so that's where they settled on using the user ID for their partition key, is because most of their queries are on, what are the tweets for this particular user, as well as the fact that, it's not always just a single user tweeting, but for any given time, there's many, many users tweeting. that this allows me to distribute my workload across many partitions for writes, while also being able to preserve queryability and serve reads out of a single partition. So this kind of gives you an idea of how you want to choose a partition key. The other pattern that I thought was really interesting that is good for you guys to know is how do you do search with text? And one of the mechanisms for doing this is what they wanted to do was they wanted to be able to search tweets by a term. And rather than using, let's say, a string contains, we do have like a string contains system function. When you do a string contains and you look at the index, what we do is we have a set of hash index and range index, but contains is not something that fits well in either of these models, right? So what you're going to do is you're going to do a scan across all of that data in a collection, and that's not a very efficient query. Instead, what you can do is you can leverage the fact that we have a denormalized data model and that DocumentDB can now support arrays of tags. That if you were to, and this is what Affinio did, was they used a Lucene lexer to break up that text into terms, and then you can then do an array contains query, which I have above, to look at exact matches in the terms array. And this allows them to do this query against the index very, very efficiently. I will also note that DocumentDB has very tight integration with all of our other Azure products, including HD Insight Search, Power BI, and Data Factory. If you need fuzzy text search, let's say with also spelling mistakes, we also have this thing called the Azure Search Indexer, which allows you to use DocumentDB as a source and perform search over Azure Search, which gives you the capability of then doing retrieval with even things like spelling mistakes, if I want to do search with fuzzy text. To kind of summarize what we're all about, I mean, DocumentDB gives you elasticity, low latency, availability, consistency, and global scale, all of these really awesome things. And we deliver this with enterprise-grade SLAs. It's a completely managed service. Some of the really helpful resources I found, like you can tell, like I'm super passionate about this service. I really love it. If you tweet us, if you post on Stack Overflow, or if you want to just email us, we're happy to even do like one-on-one guidance for design. Looking at designing your data model, helping you choose a partition key. Please just contact us. Like you might want to take a photo of this, say this in your back pocket. Like we will help you. I have some obligatory slides. Oh, yeah. Let me give you some more time to take this in.
And up front here, we actually have some of those flyers that talks about some of this, as well as all these details are in there too. So you could leverage that if you want to.
So I've done a lot of talking. I also want to make sure that I reserve some time to help answer questions and be here for you. It looks like there's a few mics set up on the aisle. Do you guys want to come up? And I'd be happy to answer any questions you guys have.
Hello? Hello?
Hey.
Hey, I heard an update yesterday from the Event Hubs group about automatic connectors from Event Hubs. Is DocumentDB going to be supported with Event Hubs directly to DocumentDB? Can you speak on that at all?
I think Event Hubs to DocumentDB is kind of on our longer-term roadmap. Today, the pattern for getting this immediately is using Event Hubs and using something like Stream Analytics to do the aggregation and dumping it into DocumentDB.
You said the global replication was like a minute, I thought I heard, between nodes. Is that true? What did I hear there?
For global replication, it kind of depends on a variety of things, including like how much throughput we're talking about here. This gives you an effective range. The minimum is speed of light between these two data centers. The maximum, I've never seen something take longer than 10 minutes. Okay. Typically speaking, I would say it's in the order of magnitude of seconds.
So the other question, for those of us who are dealing with SQL, the paradigm shift, no zero downtime, code deployment, schema changes, the whole 9 yards, what is the general design pattern used to basically promote database schema changes so that the app tier basically keeps running? This is completely new to me, so I know this is maybe a simple question, but what's the design pattern? So that is that a database person that does that? Devs? How does this work?
Both should be involved. Really, like some of the things that I see both parties being involved in here is schema never really goes away, right? If you don't know what the schema is, you don't know how to query that data. Furthermore, sometimes you do want to do some work in terms of changing existing records. One way of doing batch applying for existing records is to use a store procedure. Well, actually then, not only will you be able to apply batch updates very quickly, and the reason why that is because when you send like an update request on a single document, we have to act and persist that to disk. Whereas if you were to do this in a store procedure, what we can do is we can batch apply that and do that very high performant without waiting for a single record act, but rather a transactional act. Anyhow, depending on what the scenario is, this is one way of applying those batch updates. The other thing to note is we did kind of build this to be flexible on schema. And so if you want to move fast on the application, no longer do you need to keep the schema and the data model and the database and the application in sync, but rather the application can independently evolve. And if the model is there and that changes, the model is just dictated by the application. The database is flexible and will handle anything you throw at it.
So where does the Azure table store fit into all this, into the new NoSQL story?
Gotcha. For Azure Table Storage and DocumentDB, at least this is my personal opinion, and this is a bit of an opinionated answer. I view table storage as very good when you need key value access, and latency is not super tight, throughput's not super tight, but instead you're very price-driven. Because the thing about table storage is it's incredibly cheap to store lots of data in it. Where DocumentDB, I think, becomes a good fit for you is if you have very high scale or performance requirements, where you need lots of throughput, low latencies, as well as flexible query. You want, let's say, secondary index support, or you want even indexing over evolving schemas without having to deal with any effort. This is where DocumentDB support gives you a lot more capability. And so I view DocumentDB more as like our premium NoSQL offering. And then you also get things like global distribution, which I talked a little bit on the talk.
Yeah, so one of the things that we actually see internally amongst, we have a lot of, Microsoft is also building some of the biggest SaaS services, and many of them are built on top of stores like DocumentDB and Table Store. And as Andrew said, we see a lot more augmentation in terms of scenarios where they actually see low latency needs or global distribution needs, where the NoSQL store of choice is DocumentDB, but where in terms of effectively storing large chunks of data for key value access, table storage is a good thing.
And the other thing is you don't have to choose one or the other. I have also seen patterns where you can leverage both. And this is the pattern I showed with Lambda, where Lambda architecture, where you can use DocumentDB as a hot store, where latency requirements are very, very high, and then use Table Store as like a cold store, or any of the other Azure storage products as a cold store for doing like very, very long retention, where you you want to just keep records forever.
Yeah. First of all, thanks for the talk. It demystified DocumentDB for me, so that's fantastic. Talking about the IoT example a while ago, the design pattern, there's two questions that I have over there because I have a live case today. One is, why do we have a DocumentDB that's on hot? I remember from the diagram, there's Stream Analytics, and there's DocumentDB. So, and then you have cold and warm. I understand cold and warm, but why do we have the hot?
So the hot store in that scenario is to have the raw events. And so once you process a bunch of events and you prepare an aggregated view out of Stream Analytics, you lose some of that fidelity, right? So you can get an idea, like, across all of my devices that an anomaly happened, that I see a spike. But then when you want to do that fine-grained investigation of going, let me look at each device's data and their records one by one, this is where that hot store comes in and where DocumentDB is a good fit for that too.
Second part of the question is, how do we handle if the customer or the customer wants encrypted data in DocumentDB? Do we do encrypted data in DocumentDB?
Gotcha. Some cool things about encryption is we're actually working on transparent encryption at rest. Our target today is the end of the year. Kind of a funny thing about doing software estimates and time. It's hard, right? So I mean, please don't hold me to this too firmly, but we are targeting end of year
Yeah.
for transparent data encryption. The other thing is if you have immediate needs, one is please contact us. We might be able to hook you up with a private preview when available. The other thing is we've also worked with a lot of people on doing client-side encryption. So if there's like just some PII inside that within the document, you can always encrypt that, on the client-side application.
The comment there is that because customer is really interested because of the capabilities of SQL 2016 row-level encryption. That's the reason why they were looking for it.
So yeah, transparent data encryption at rest is coming. And I should also note that at least encryption in motion, that's already done. We actually don't allow you to establish an unencrypted connection with DocumentDB. We use, I think, TLS 1.2 or SSL.
Is there any update on the status of a possible on-premise version for DocumentDB?
For on-premise, the other thing that we're working on our short term is a local emulator. So for dev test scenarios, by end of year, we will have a local emulator out there, hopefully. Same comment about software estimates, but that is our target and our intent. Longer term for on-premise deployments, I mean, I think Azure Stack will be a matter of when, not if.
Yeah, so I think, Andrew talked about that. In terms of the local emulator, it's primarily a dev test scenario. I mean, if there is an interest, you can, again, send us a note, and we can try to actually get you an earlier preview. We plan to be completely in Azure Stack, and Azure Stack is our on-premises story for that. The one other scenario that we have actually seen customers today, we've worked with a certain set of customers who are actually using Mongo on-premises in terms of their applications, and then moving to DocumentDB with the Mongo protocol support. That's not our official answer to it, but
yeah, that's what we're looking at right now. So, okay, thank you.
All right, so I got two questions. One is more of a technical question. One's more of a non-technical question. So I'll start with the easy non-technical one. We had we're looking at leveraging quite a bit of DocumentDB, and we had some questions about how with georeplication the request units are allocated. So, and that is like, so if I get 100 request units and I geo-replicate over 10 different regions, does that mean each region gets 10 request units? Or is that 100 request units across all of the regions? But then am I paying like 10 times my 100 request units? How does that kind of work?
Gotcha. You are allocating request units into each region. Now, one thing to note is if you have, let's say, a global user base, and in order to serve this global user base, I need, let's say, 1 million request units per second. Rather than having, let's say, 1 million in one region and then having 1 million in each of the other regions, because we give you the elasticity to be able to dial throughput up and down, if you realize that you need, let's say, 500,000 in this region and 500,000 in this region, what you can do is you can dial down to 500,000 and have 500,000 in each region, right?
Okay, so basically bulk buy and then allocate per region.
Yeah.
Okay, so the second question is more of an architectural thing. We have a case where we'd like to leverage a shared collection or shared document database. We like to do the georeplication features. The problem is we have inputting customers or writing customers in multiple regions. So we can't be like, hey, we'll have the primary write region as US, but then we have Australian customers who also need to write into the same thing. So do you have any suggestions on a good way to handle that?
Yeah. So I guess two comments. One is long-term, our vision is to enable multi-write regions. And the likely way we will probably do this is you can define partition keys. So if I know that these tenants are in one region and these other tenants are in a different region, that you can home tenants into different regions. Shorter term, what we can do is we can help you design a solution, whether that is having multiple DocDB accounts managed by the same RBAC permissions on the Azure portal, and having those homed in with different write regions. Or we might also be able to help you come up with other design patterns based off of your scenario. I highly recommend you just reaching out to us. Give us a shout over email. We can do kind of like a one-on-one guidance, and that way we can custom tailor a pattern just for you and your scenario.
Okay, but it is a scenario that you guys are certainly looking at?
Oh yeah, absolutely.
Sweet, awesome. Thank you guys very much.
So one thing I would suggest is it doesn't have to end here in terms of, I think we have Microsoft Virtual Academy videos, we're doing webinars. Connect with us and let us know what topic is of interest. We can go into the details. We're trying to get more and more, understanding more and more patterns, working directly with customers. We believe we have really good tech. We believe that it can actually solve a lot of problems and build modern applications. So let us know how we can help, and we will help you. Thank you.